Hello everybody! Welcome to FlexLogic's EFLX eFPGA demo session. Here is today's agenda. I'll start with a very brief overview of our company and technology. After that, I'll do two demos. One is the binary neural network demo on our TSMC 28HPC Plus Eval board. And the other one is the modular FPGA demo on our TSMC 16FFC Eval board. Now, let's get started. FlexLogix is a startup company founded in 2014. Our most innovative eFPGA technology won the 2014 ISSCC Best Paper Award. In the past 6 years, more than 20 patents have been filed worldwide. We now have two main product lines, EFLX eFPGA IP and NMAX AI Inference IP and chip. Our focus today is the EFLX eFPGA hard IP. Our EFLX is a hard IP that can provide high logic density and performance. It is designed as an IP for easy silicon integration. It is super scalable and has the best metal stack compatibility. It usually takes us only 6 to 8 months to port to any new process, since we use the foundry standard cell-based logic design. Now, EFLX has been silicon proven on multiple process nodes by both FlexLogix and our customers. We always build test chip and eval board when we port to a new technology node for our validation purposes. These boards are also available for our customer evaluation. I'm going to use the two boards shown in the picture here for our demo today. Before I start running the demo, let me first give you a brief introduction on the BNN model and how it's implemented on our EFLX eFPGA. In a BNN model, all the weights and data are binarized. It is a promising technique for deploying deep models on resource-limited devices. The reason for that is the complex matrix multiplication function in a BNN model can be easily transformed into an XNOR operation when implemented in hardware. After the XNOR operations, you can simply use a ones counter to get the result of the matrix multiplication function as shown in the figure here. In this demo, we're using a single fully connected layer for handwritten digits recognition. The original model uses a 16 by 16 image. We resized the input image to 28 by 28 and retrained the model in TensorFlow. The network was trained using the MNIST training dataset. Our demo today only uses two sets of the numbers shown here. Now, let's switch to the run directory of the demo. On the bottom right side here, I'm also having a camera taking the video of the eval board. The TSMC 28HPCP test chip is right here inside the socket. The power is connected, so these red LED lights are on. The mini USB port here is also connected for downloading bitstream from my PC. Now, let me double-click on this to start the demo. Now, let's go to our second demo, the modular eFPGA demo. The modular eFPGA modularized the eFPGA array into consistent containers with the same resources. The analogy is like Linux containers that are self-contained execution environments that share the kernel of the host operating system. Each modular eFPGA container block has its own dedicated resources, including one EFLX core, high-speed local memory, access to system memory, and access to the chip I/O matrix. Below is the basic modular eFPGA container block. The modular eFPGA array can be connected to the rest of the SoC via system interconnect fabric, such as an AXI or AHB bus. Each container block in the modular eFPGA array can be swapped out by the SoC program by partially reconfiguring the array with a new functions bitstream. Today, we're using our TSMC 16FFC validation chip to implement the modular eFPGA. The design function is programmed into the 7x7 eFLX 4K array of the validation chip. The FlexLogic's proprietary virtual array feature enables us to partition the design into two parts. The left part, shown in this figure, is the fixed function of an MCU subsystem. The right part is the modular eFPGA array. It has been programmed with three accelerator functions. The AES functions connect to the MCU via the AHB fabric as masters. The SHA function connects to the MCU via the APB bus as a slave. The demo you'll see in a minute will show that the AES functions running on the modular eFPGA can run hundreds of times faster than running in software by the ARM Cortex-M0, and that the SHA accelerator runs 25 times faster on the modular eFPGA than running it in software. Let's take a look. Here is the run directory and the eval board. Our TSMC 16FFC test chip is in the socket at the center of the eval board. The power is on and the mini USB port is connected. The design bitstream will be downloaded from the PC to the eval board through this mini USB interface. For this demo, we're also using the PMOD connector here to capture the data generated by the test chip and then send them back to the PC. Now, let me double-click on this to start the demo. The bitstream configuration just started. The bitstream configuration is complete now. We can see data showing in this teraterm window here. The first test we run is the AES encryption and decryption. As you can see, it only takes 18 microseconds to encrypt 256 bytes of data on the modular eFPGA hardware, and the decryption takes the same amount of time. Then we ran the exact same design in the software. As you can see, to encrypt the same amount of data, now you'll need 3,700 and 80 microsecond. To decrypt these data, you'll need another 28,380 microsecond. This is more than 1,500 times more than the time you'll need for decryption in the modular eFPGA. After the AES test, we're also demoing the SHA-256. The hash time on the modular eFPGA hardware and the software is 16 microsecond and 400 microsecond respectively. Now let me quickly show you our embedded logic analyzer and how to use it to obtain more visibility inside your chip. First, I'll set the ELA trigger for the AES encryption. The ELA is now configured and triggered. 64 samples are captured. Now let me read the captured data out. You can see a VCD waveform file was just generated. Let's open it up and take a look. The ELA was triggered when the input data were loaded. Here you can see the output data of this AES encryption function when the done signal was asserted. Now let me go back and trigger the ELA for the AES decryption function to see if the decryption function is correct. As you can see in this waveform, when the done signal of the decryption design was asserted, the output is the same as the input of the previously shown AES encryption design. Thank you for watching the FlexLogic's eFPGA demos.